This is the key to exam 2 that I gave on Friday. 9 people took the exam, and several of them did very, very poorly on this. So I've written the key here, and I will quickly go through what I saw as the main mistakes on each problem. Number 1, it was algebra. Everybody tried to use L'Hopital's rule, but going from here, this green arrow here, going from 1 plus 1 over x over 2x to this expression, people couldn't do the algebra. So notice here, you just multiply the top and the bottom by x. Therefore, you get rid of the denominator. So you get x plus 1 over 2x squared. Take L'Hopital's rule again and get a limit of 0. The next problem, problem 2, again, a lot of this was just algebra, and you know, to get a grade in Calc 2, you have to be proficient in algebra. The first one, many people noticed that 0.9 to the n would converge to 0, but you said the whole thing did. This is a sequence, not a series, 5 minus a term that goes to 0. So, in other words, you should notice that went to 0, so the limit was 5. And this went to 0 because the absolute value of 0.9 is less than 1. The next one, generally everybody got this. You squeezed the nth term of the sequence b sub n between 0 and 1 over n. Some of you said minus 1 over n and 1 over n. That's fine too. And we see that on the left-hand side we have 0. The right-hand side goes to 0 as n goes to infinity. So b sub n then has a limit of 0 by the squeeze theorem. C, again, algebra. Most of you saw to divide by 4 to the n. And most of you here said 3 over 4 to the n minus 4 to the n over 4 to the n is 1. But then down here, I don't know what happened. You divided by 4 to the n twice, and some of you added 2 plus 7. This is 2 over 4 to the n plus 7 times 4 to the n over 4 to the n. So do that again and see how that cancels. The limit was minus 1/7. The part D I suspected would be tricky. This is trying to see if you understand the difference between the sequence, the two sequences related to a series. Here, Sn is the sum of the first n terms of the geometric series given. So if Sn is the nth partial sum, you know that the limit of Sn as n goes to infinity is the so-called sum of that series, which is first term over 1 minus r, is 3/2. Problem 3, what does it mean to say that the series converges? Well, we've said this a million times. It means that the limit of the sequence of partial sums exists. The sum of the series is the limit as n goes to infinity of Sn. Number 4, why can we be certain that this series diverges? Well, by the test for divergence. An does not go to 0. 5, evaluate this. Here you had to look at it as the sum of two geometric series, which you can do if both of those series converge, which they do. So see how I've split it into two series here, and that is because, let me write up here, that's because 2 over 5 to the k plus 3k over 5 to the k. That's what this is equal to. And then that would be 2 times 1/5 to the k and 3/5 to the k. So then you use the first term over 1 minus r, add them together, and you get 2. Number 6 was using the integral test So I gave you one that was very easy to integrate. Over here on the left, right here, I first found the antiderivative, just like on scratch paper. Letting u be ln x, du is 1 over x dx. This is the integral of u to the minus 2 du, which is minus 1 over u. But I want to put it back in terms of x. A couple people left it in terms of u. That's a common mistake that any of us can make. But remember, we are going to evaluate this integral between x equals t and x equals 2. So put your integral in terms of x. Don't leave it in terms of u if you used a u substitution. So using the definition of an improper integral, we know that this will be the limit as t goes to infinity of the definite integral from 2 to t of our integrand. And here I integrated it next, and then I saw what the limit was. I plugged in t, plugged in 2. I saw that as t goes to infinity, this first term in the sum goes to 0, and the second term is just a number. So since the integral converges, so does the series by the integral test. The next problem had, I guess, 3 parts to it, and in each case it turned out you use the comparison test. What you do if you know that you're going to be using the comparison test, is you try to find the comparison series. And it's usually, in fact almost always, it is either a geometric series, which does or does not converge, or it is a p-series. Now in part A, if you throw out all the unimportant stuff, if k is 10 billion, we don't care about the minus 3. If you throw that all out, over here in the red, I have found the comparison series first. So you just have the square root of k over k, which is 1 over k to the 1/2. Now we know that that series, sigma 1 over k to the 1/2, diverges. So we're going to hope that we can get this above 1 over k to the 1/2, and then we know that we can get divergence. So I did these inequalities on the key in several steps. You could start right here if you see it. Why not? You just made the denominator. You just start right here and you say this is bigger than the square root of k over k because I made the denominator bigger. And that's 1 over the square root of k. Sigma 1 over the square root of k diverges. So since my nth term was bigger than its nth term, the series diverged by the comparison test. The next one, now this is a lot of you did this. You said that your term, whoops, I have to get plugged in. You said, well, this term, I'll just put a sub k. You said it is less than 4 over k factorial. And really that's fine. You could say it's less than that, and then you would have to say sigma 4 over k factorial is, you'd have to show that this converges, because this isn't a p-series. It's not one that we automatically can characterize as convergent. So you'd have to say, well, that's equal to 4 times 1 over k factorial, and that would be, you could pull out the 4, and you'd have sigma 1 to the k over k factorial. See, it's e, so it's 4e. It converges. The easiest way to do it is over here on the left-hand side. I said our term, our a sub k, is less than, instead of 4 over k factorial, I used 4 over 3 to the k, which is 4 times 1/3 to the k, giving me a convergent geometric series. Either way was fine. But you would have to show in this case that that is a convergent series. part C, again, I just eliminated everything that wouldn't make any difference when n was huge. And so we would just have n squared on the top, and on the bottom, n cubed to the 5/3, which is n to the 5th. So we get a p-series, sigma 1 over n cubed, and we know it converges. So I set out to hopefully get this term, a sub n, underneath the convergent p-series. So actually, you could just start right here if you see this. If you don't, you start very, very slowly, and you know, with your denominators. But you know that n squared over this denominator will be less than n squared over n to the 5th, because you have subtracted 4 inside this quantity that you're raising to the 5/3. So you've made the denominator a little bit smaller, and therefore increased the fraction. So we have our a sub n underneath 1 over n cubed, and sigma 1 over n cubed converges with p equal to 3. So the series converges by the comparison test. Here we're finding the sum of the series, and you look at that little list of known power series, and you see in part A, clearly that's x to the m over m factorial, but x is equal to 2. So this is e squared. Part B, clearly this is going to be a cosine. If you look at the cosine on the list I gave you, this looks just like cosine x, except we have 9 to the k, and we need something raised to the 2k, x to the 2k. Well, 9 is 3 squared. So 3 squared to the k is 3 to the 2k. And so we see that our x is 3, and this is simply cosine 3. Number 9, what does it mean for a series to converge absolutely? If you had to memorize the definition, it means that sigma absolute value a sub n converges. It's a strong kind of convergence when the series of absolute values converges. Number 10, find the interval of absolute convergence. Okay, well, this was using our ratio test, so you had to take the absolute value of the n plus first term over, or times the reciprocal of, the absolute value of the nth term. And everyone that took this set this up correctly. But then again, algebra. So you have x to the n plus 1 over x to the n gives you absolute x. 3 to the n over 3 to the n plus 1. Well, 3 to the n plus 1 is 3 times 3 to the n. So the 3 to the n's cancel, and you have the absolute x over 3 times. Now, this is n squared over n plus 1 squared. And a squared over b squared, we often would rather write as a over b squared. So I looked at this as n over n plus 1, the quantity squared. And we know that n over n plus 1 goes to 1. So this limit, now when you draw this arrow, that means you're taking the limit as n goes to infinity. It converges to whatever the absolute value of x is over 3. Now, we want this limit here has to be less than 1 in order to get convergence by the ratio test. So we take the limit, set it less than 1, and quickly solve for the interval of convergence. The second part, again, we do the same thing. Absolute value of the n plus first term times the reciprocal of the absolute value of the nth term. Again, we have our absolute value of x minus 4 canceling, leaving us 1 on the top, 5 to the n on the top, 5 to the n plus 1 on the bottom, gives us just one factor of 5. And here again, n factorial over n plus 1 factorial. N factorial over n plus 1 factorial is this. The n factorials cancel, and we have 1 over n plus 1. Now this factor goes to 0. So 0 times this, no matter what x is, it will be 0. as we take the limit as n goes to infinity, we get 0 regardless of what x is. So it converges for all x, and the interval of convergence is the whole real line. The last problem, you had your power series for sine x, and I asked you here to find a power series for the sine of x squared. Most people did fine on this, except when you plugged in x squared, you added 2 to the exponents. And I can't give credit for that. When you take x squared, and then you cube it, it's not x to the 5th, it's x to the 6th. X to the m raised to the n is equal to x to the mn. X to the m times x to the n is x to the m plus n. These are basic rules of exponents that you should have known in the 6th grade. So look at these, make sense out of them. You can't do things like this as you go on into your upper division courses and go on out into the workplace. So anyway, you knew to plug it in. I gave you some credit for that, and then this is what you get here. The interval of convergence is minus infinity, infinity, because we know that the sine x converges everywhere. Now, for the function sine of x squared, we can't integrate that using the fundamental theorem of calculus because we don't have an elementary antiderivative. In other words, antiderivatives for the sine of x squared, which we know exist, they are not expressible in terms of your regular transcendental and polynomials. So you can't integrate that way. So I ask you here to find an antiderivative which is a power series. And most of you took whatever you had in part A and you did integrate it properly. So I gave you full credit for that. I just took off for the horrible algebra mistake there. So, okay, so you integrated it and you got, just notice, compare up here, sine of x squared, and here you have the integral. So you can look at that as you study this. And in part D, again, several people got this correct. I said, well, so we don't have an antiderivative, but we know that this series here, this integral, this series, converges for all x. Well, it turns out that if you take just the first 3 terms of this and estimate the antiderivative, estimate the antiderivative with those first 3 terms only, you have then that the integral from 0 to 1 would be, well, those first 3 terms evaluated from 1 to 0, and this is the correct number here that you get. Again, if you integrated the wrong series and evaluated it properly, I gave you full credit on that part. So I hope this helps. I'd love it if you have any comments as to the quality of this video, because I'm trying to use my new computer and new equipment to make videos. So any comments you'd have, I'd appreciate very much.